Let's wait for the bell. I have some echo. Okay, let's get started. I'm Mohammed. Welcome to lecture 3 of Seminar in Computer Architecture. As you may know, I'm also one of the instructors in this course. I'm a senior researcher and lecturer working with Professor Mutlu since 2021. And my research interest basically includes computer architecture in general, but with a much focus on near data processing, storage system design, interconnects, and heterogeneous system architecture. So today we're going to have 2 lectures, like lecture 3A and 3B. So first I will start, actually I'm continuing the part that Professor Mutlu has been teaching. And hopefully we're going to finish this part. And then next, one of my colleague, John Furtina, he's going to teach about genome analysis. Before we dive into this lecture, I'd like to announce that we almost finalized the assignments for the paper presentation, and hopefully we're going to announce it soon. The first session is going to be on October 17th, if I'm not mistaken. Is Lenny here? Is it October 17th, Lenny? Yeah, so basically we need to find a plan for next week, but we want to have basically want to have at least 2 weeks for the first presenter. So that's why we push the basically presentation by 1 week. And I'm actually quite excited about the paper assignments. I think we're going to have a lot of interesting discussions in this course. Any questions or comments? Have you submitted homework 1? Great. Okay, so yeah, let's then start. Basically, we've been discussing about future of computer architecture and hardware security, and I'm gonna continue from the part that we left off. We talked about different stuff in computer architecture and hardware security, and then we reached to this important paradigm, processing inside memory and storage. And we discussed that this is actually quite essential in order to fundamentally improve energy efficiency and performance in computer systems. And today's systems are bottlenecked by data because we are moving data a lot. And most of the system is just allocated to storing data and communication of the data, like communicating. And the processing is happening only in some specific part of the system. So we discussed about the fact that we need a balanced design such that you can use the whole system to process, not only a small part of the system. And this is the paradigm of processing inside memory or storage. And we discussed about this, like in this slide, that essentially we think about having like memory and storage that you can store your applications like database, graphs, and media. And processor can just send some queries like, do this application for me, and memory just handles that application and sends back the result. And of course, there are a lot of many important questions that we need to answer, like how do we design the compute-capable memory and controllers, processor, communication units, software and hardware interface, algorithms, theoretical foundation, and so on and so forth. And basically, we discussed that in order to get to this basic good answer to these questions, we need to look into the this transformation hierarchy in detail. Like we need to do research across the entire stack. We discussed that we have 2 variants of processing in memory, like processing near memory and processing using memory. Like in processing near memory, we have the separation between logic and memory, but we discussed that how we can move the logic closer and closer to the memory. So it can be closer like in cache, it can be in the memory controller, it can be closer to the DRAM banks or inside the banks near subarrays and so on and so forth. But in processing using memory, we want to use like the memory to do computation. So we are benefiting from analog perspective of the memory to do computation. And we're going to see some examples today. We also show this basically processing memory landscape today, that there are a lot of effort in industry as well, that we have some prototype as well as a worldwide, real world processing memory systems like OpMem system, that they can provide some kind of processing memory capability. So some of them are general purpose like OpMem system, but some of them are more specific to some applications like machine learning, like Samsung designs. But now I'd like to discuss a little bit about basically the opportunities, like the advancement in the technology. One of the reasons that we have more processing memory designs in these days. So one of the reasons is actually that we are much bottlenecked by data and also energy. So we really need to look into such solutions. But another also angle of this processing memory is that the new technologies are also enabling processing memory more and more. So one of the interesting advancement in technology was this 3D architectures in memory, such that you can provide huge bandwidth, I mean much higher bandwidth to the logic using these TSVs. And it has been also improved with new technologies as well, like monolithic design or hybrid as well as hybrid bonding. But in this work that we have done, we wanted to see this opportunity from 3D stack design and how we can use that in order to improve the performance of graph processing. So if you are basically aware of graph processing, most of the time they encounter a lot of random memory accesses. So you cannot really benefit from cache locality more or less, because usually you're going to access data randomly and it's very hard to predict the next access. So, and at the same time, it's random, and also the amount of computation that you are doing by every single data is also limited. So flops per byte is also low, such that you cannot amortize the overhead of bringing data to the system. So that's why memory-centric computing or data-centric computing is always a good fit for graph processing. In this work, Tesseract, we use this HMC, like a hybrid memory cube, that provides basically quite a lot of bandwidth to the logic unit. But the problem with HMC and this 3D stack memory in general is that the memory capacity is not that high. That's why we need several of these 3D stack memory putting together and connect them in a network. And this is also quite similar to what is happening in GPU design today as well. Like GPU has high bandwidth memory, HBM, and then one GPU has like 4 or 6, I don't know, stacks of HBM, and you can keep data on them, but that's also not enough. So you need several GPUs in order to also provide enough memory for them. So here also the way that we design this Tesseract is that we consider that we have several cubes here, like in a mesh, like in a grid, let's say, but and there has been an interconnection network across them. I'm not going into detail of design because there are a lot of design choices in this Tesseract that you need to basically check the paper for that. But essentially, it's basically the host processor this graph application is non-cacheable. So meaning that processor is not doing computation on that graph. So the graph processing is only mapped to this Tesseract system. So these are cubes that they are connected in a graph, and then in each cube we have this network like this HMC cube, and in each HMC cube we have these like several vaults, and per vault we have logics as well as memory. So each logic has a basically exclusive memory that has access to his data. So whenever we need data which is stored in another cube, in another vault, let's say, instead of bringing data from that vault to our vault, we can just send our instruction. Like for example, you need to update the data, you need to update the value. Instead of bringing that data or that page to your memory and then update it, you just send the instruction to that unit. And that can heavily reduce the data movement communication in Tesseract. So yeah, so that was the overall, view of this work. And with that, we show that we can provide huge performance improvement, like around 13 times, as well as energy reduction. So if you want to learn more about Tesseract, I would suggest that you check the paper. This paper has been also selected in 25-year retrospective ISCA in ISCA 15. That if you want to, if you're not patient enough to read the whole paper, you can also check this short retrospective paper that you can give some insight about this work to you. So, but that's the work in Tesseract. We just try to use processing near memory in order to accelerate. But the next works, like in this SISA, we wanted also to see how we can enable better performance by changing the instruction set architecture. So graph applications, there is a chance that we can use set algebra as well as linear algebra to improve the performance of them. And it turns out that actually using linear algebra and set algebra are actually quite good for processing memory. So in this work, we show that if we use set algebra, we can basically implement many of these graph mining algorithms. And so then your graph algorithm is going to be translated to set union or set intersection. And those instructions can be easily implemented in processing memory. So with that, while we are basically working through the entire stack, like changing how we implement the algorithm, and also the hardware support in processing memory, you can actually implement much better performance. You can have much better performance for graph processing. So it's another good example that how like doing basically research through the entire stack of computing can enable much better solutions. We also look into other applications. Like also I want to emphasize here that when we look into processing near memory, we usually have a top-down approach. Like we know that this is an application, this is an important application which is overwhelmed by data, and we want to accelerate that application fundamentally. So then we try to map this application nicely on a processing near memory technology. So then it turns out to how you're going to address a lot of system-wide challenges, like the algorithm implementation, how you synergize the whole system. Also, that application might have several steps, so how you basically make them coherent. So that's the way we usually look into processing near memory. But processing using memory that I'm going to show later is actually like the bottom-up design, that we have some opportunities, and then we want to see how we can benefit from these opportunities to enable applications. So we're going to see later also with some examples. But here I'm giving some examples about processing near memory. So I already talked about graph applications. Here is about neural network inference. So we look into basically Google neural network models for edge devices. And you know that we have this tensor processing unit, TPU, that is being used for such things. So we show that basically, so we observe that this Google TPU, the performance, the utilization is not really good. And we observed that the reason is that basically it's a kind of monolithic design with the mindset of one design should fit everything. And that caused a lot of issues. As we showed in this work is that what we showed here is that basically we have significant variation in terms of layer characteristics across different models. So if we studied the different models and we show that basically in terms of, so this graph shows flop per byte and also parameter footprint. So flop per byte shows basically the arithmetic intensity of your application. So when you have higher flop per byte, probably you can amortize, basically your application is more compute intensive. And also when you have a less parameter footprint, meaning that you don't read much data, basically. So when the application is this part, like the layers are in this area, you don't read much data, and you're doing a lot of computation on them. So meaning that compute-intensive kernels or compute-intensive, basically, design can like compute-centric, like CPU-centric or GPU-centric design can be a good fit for them, or accelerator system. But for these kind of these layers here that you can see that basically they have huge parameter footprint, I mean, much larger. And also the flop per byte is also lower. So that means that these layers are more memory bound, and they are a good fit for basically memory-centric computing. We also show that as a second insight that even within each model, so the previous study was across models, but even each model, we also observe that we have significant variation in terms of layer characteristics. So if you consider the number of MACs, you can see that we have the variation in MAC intensity up to 200 times across layers. And if you check also flop per byte, you can also observe that we have up to 244 times across layers difference. So that clearly shows that if you design a single system, like a single accelerator that should work for everything, then you're gonna have basically low utilization and also low performance. So the idea of Mensa is that instead of having a monolithic processor-centric accelerator, we can have a heterogeneous accelerator that combines different accelerators. So one of them is more, let's say, processor-centric. The other two is more like memory-centric. But you need to read the paper to know basically the exact difference between them. And then there is a runtime system that characterizes models on the runtime, and based on the characteristics of them, categorize them in different families, and then we map each family to appropriate accelerators. So that's more or less the key idea of Mensa. So we observed that by checking these flop per byte of different models, we can actually group them in 5 families. So family 1 and 2, you can see that they are actually more or less for compute-centric layers. So you can map them to basically CPU, GPU, or the circuits like processor-centric accelerators. But families 3, 4, and 5, they are more memory bound, so we need to use data-centric computing to accelerate them. And with that, we show that Mensa can reduce energy consumption by 3 times compared to the baseline edge TPU, and also improves the inference throughput by 3.1 times compared to edge TPU. So yeah, so that's Mensa. And if you want to learn more about it, you can check the paper. We also look into Google workloads for consumer devices. This was one of the earliest work that we have done for mobile devices, and we show that around 60% of the energy of the system is consumed only for moving data. And we studied different mobile consumer workloads like browsing, like Chrome web browsing, as well as video playback. And we observed that. And then we use processing memory system in order to reduce the cost and energy consumption for them. But that's all about processing near memory. You can actually see much more from the works that we have done in Safari, from Professor Mutlu website, as well as also the course that we have for memory-centric computing that's gonna kick off next week. Now I want to look a little bit more also in processing using DRAM. As I said, when you work on processing using memory in general, we always try to find the opportunity that you can do some computation. And then the next step is that how we can benefit from such computation in order to provide support for more sophisticated applications. So here, for example, we are discussing about processing using DRAM, and we can support bulk bitwise and or not or majority gates. We can do bulk bitwise copy or like initialize or let's say reset the whole row like 0. We can also generate true random numbers, and we can also generate physical unclonable functions that can be used as a signature of your device. And also we can do more complex computation using lookup tables. So that's also a key here, that the benefit is not only limited to such simple operations. So you can also use DRAM in order for lookup tables, and that you can bridge the gap between processing using DRAM and processing near memory. And the good thing is that all these things are happening with low cost. And so it's only with using analog computation capability of DRAM. And the idea is that we want to activate multiple rows to perform computation. And this is possible even in commodity off-the-shelf DRAM chips, that Ismail has done a lot of works in that line. So you can talk to Ismail if you want to learn more. So yeah, so as a summary, bottom line result, we observe that we can have like 30 times to 257 times, I mean, depending on different papers actually, performance and energy improvement, and these are some sample works. But now let's quickly also look at them. Like this is an in-memory copy. So previously, like in processor-centric design, if you want to copy a row in memory, in DRAM to another row, which is actually a common also kernel, you need to read that row, cache block by cache block, move them to the caches and then to the CPU, like byte by byte or word by word, do a like copy, and then you need to store it back. So there are a lot of data movement happening, and the computation is just moving one register to another register, which is nothing almost. So the way that we design is just, you know, copying one memory line to another line by providing support inside the memory. So you just need to do 2 consecutive activation in the memory, and that can basically provide this memory copy. And it provides low latency copy as well as low bandwidth utilization. So we are not consuming or wasting, let's say, this bandwidth for this copy. So we're going to use this bandwidth for something which is more necessary. And also we have much less cache pollution, or let's say no cache pollution, because we don't pollute cache for data copy, and no unwanted data movements. And this is the result. If you want to basically copy data from processor, and it turns out that using in-memory copy, we can reduce this around 1,000 nanosecond to only 90 nanosecond. And it also reduces a lot of energy consumption. If you want to learn more about row clone, I would suggest that you check the paper. There are a lot of also other stuff in row clone, as well as future works that we look into it, how we can provide data copy between subarrays, which is Lisa work, as well as also in memories that they have a lot of banks. And for that, we like HBM or HMC, that we have several, the number of banks are much more. So row clone in those memories is not that easy. So we show that how we can benefit from network on memory in order to provide data copy across banks. So you can also check those papers if you are interested. But to do computation, we can also do in DRAM and OR using triple row activation. So this is also our observation, that we show that if we activate 3 rows at the same time, as long as 2 of these rows, or let's say here, these are cells, basically, we are activating 3 cells at the same time. So when you are activating all of them together, this bit line is gonna have the charge sharing of all these cells together, right? So as long as you have 2, let's say, high voltage in 2 cells, the outcome would be something a bit higher than VDD half, which is enough to make, you know, such that sense amplifier can make it to full VDD. And then you have VDD in whole. So this is, if you want to write the equation in Boolean algebra, you can have this final state that the value stored in the bit line, as well as also in the whole, in all these 3 cells, is going to be AB plus AB or BC or AC. And then you can also formulate this equation to this equation, like C and A or B, and not C, A, B. And with that, you can easily also implement OR and AND operation. So this is the majority function. But if you put by basically controlling the value that you have in the cell C, you can do AND and OR operation. So this is the work that we showed in this CAL paper in 2015. But then after that, we also extended in a conference paper by supporting NOT operation, as well as addressing some other issues. This is AND bit paper that you can take a look and read about it. But the interesting thing is that existing DRAM chips are already quite capable. So you can, yes.
I have a question on the previous slide. So can you use this one? Yeah. Okay. So the previous slide. Yep. So here we have A, B, and C all open. I mean,
Open, you mean, yes, they are
use the
activated.
data, so, and all of them get overwritten.
Yes,
So you lose
that's
the
true.
data in A and
It's
B,
destructive, yes. So you need to basically, yeah, you need to copy them. If you really want to make sure that if the previous data is important, sometimes they're not really important. There are some intermediate data in your function, and you want to immediately consume that, right? So that is not really important. But if there are some data that you want to keep it, yes, you need to copy it somewhere. Okay. But you can use row clone again. You don't need to move it to CPU and then copy it, right? But that was a great question. Yes.
I know this was specifically about bulk data copying and doing arithmetic on those, but do you think it's possible to do also more granular copying or arithmetic in DRAM chips?
Low granularity copy, you said?
No, more granular. So, for example, that you can put on bit masks such that some rows won't get affected when we do a clone.
I'm not sure if I understand. Ismail, did you get? Yeah.
So you wanna ask that normally what we do is in row width, right? 8 kilobyte. Do you want to have more fine grain?
Fine grain or? Yeah, so fine grain, yes, we have also papers, Figaro, if I'm not mistaken, right? That we do row copy at the guarantee of cache block. Is that correct?
Yes, also in MIM DRAM as well.
Also in MIM DRAM, true. Yeah. So I can send you those papers if you are interested. Thank you. Any other questions? Great. Yeah, so I was here that interestingly, like existing DRAM chips are already quite capable. So in Ambit paper, we use simulators as well as also transistor level simulation like HSPICE in order to show that this is possible. But later on, some other groups, as well as our group also, we observed that we can do these operations even using commercially off-the-shelf DRAM chips. So this is the work PyDRAM that Atterberg leads this project. And we show that, so we provide end-to-end row clone and TRNG through random number generator using off-the-shelf DRAM chips. So the idea is that we need to violate DRAM timing parameters to mimic row clone. So normally in row clone, we need to send 2 activation commands back to back, right? As we discussed. But in the DRAM chip, if you send 2 activation commands back to back, the second one is going to be ignored because the controller that is inside, like the FSM, needs one pre-charge. So there should be one activation, then should be pre-charge, and then another activation. So you cannot send 2 activation commands. The way that we can implement row clone, for example, in DRAM, like commercially off-the-shelf DRAM chip, is that by violating timings. So you send activation, and then you send a pre-charge. But then for that pre-charge, you don't wait as much as you need to wait. So you just send it, and then you violate it and send another activation. So by that, you can mimic that you are sending 2 activation commands back to back, and you can implement row clone. Of course, it might not be completely, let's say, reliable, but it's good to show that even commercially off-the-shelf DRAM chips are capable. Yes?
So to do that, you only have to change the memory controller that controls the DRAM, or what would you have to change?
So by violate, you mean to violate timings? Yes. Because memory controller is supposed to obey the timing of the DRAM, so you can. And with this, our infrastructure DRAM bender, for example, you can actually play with timing parameters. Is it correct? That's fine. Yeah. So in PyDRAM, we show that we can. So this is a FPGA-based system, and like end-to-end system that we show that we can implement row clone and TRNG using off-the-shelf DRAM chips. And this is basically the prototype that we have prepared. If you are interested, you can also check the GitHub page as well as also the talk and the paper of PyDRAM. So, and these are the results that we show that we can actually provide by using providing in-DRAM copy and initialization. You can improve throughput by quite a lot, by 120 times as well as 89 times. But this is also a bit skewed because the processor that we have in FPGAs are not that powerful. So if you are implement such technique in a real system, not real, I mean, this is also real system, but I mean, in a more, let's say, powerful workstation, still you're gonna see improvement, but improvement might be a bit lower. So yeah, if you want to more about PyDRAM, you can check this paper. This is even more interesting that this work we published in HPC 2024, that the SMILE showed that we can do functionally complete Boolean logic in real DRAM chips, which is quite fascinating. So before this work, people basically could do like row clone, they could do and OR operations, but NOT was not really supported. And when you don't have support for NOT operation, you cannot do functionally complete Boolean logic. So SMILE showed that basically we can do these, basically we can have such support in commercial off-the-shelf DRAM chips, like we can simultaneously activate up to 48 rows in 2 neighboring subarrays, and we can perform NOT operations with up to 32 output operands, and we can perform up to 16 input and NAND OR and NOR operations. So these are the observations that we had in that paper. So the key idea for NOT operation is that like the source row is in a subarray, and the destination row is another subarray, and these two subarrays are sharing the sense amplifier basically. So, and in sense amplifier you have basically these back-to-back NOT operations. So you need to basically activate the source, and you can see that when you activate the source, you have the NOT of this source on this line. So if you activate the destination row, then you're going to have the NOT of A to the destination row. So that's why we can implement NOT operation. And interestingly, it's not only by this figure. I mean, we can do it with real DRAM chips, as SMILE showed in his work. And also, you can manipulate the bitline voltage to express a wide variety of functions using multiple row activation in neighboring subarrays. So like here, you can have several rows, as well as also in the source subarray, you can also have several rows, and then you can do multiple row activation. So after doing multiple row activation in this subarray, you're gonna have a basically voltage of XY, which is like a result of charge sharing of all these rows that you activate. And also in the upper subarray, you're also gonna have these like V, A or B, which is A and B, which is again, charge sharing of them. And then using this sense amplifier, you can compare VAB and VXY. And if you handle these values smart enough, you can implement and or NAND and NOR operations. If you want to learn more, at this moment, you can ask SMILE. Is there an easy way to explain it quite fast?
This one?
Yes.
Is there an example in the next
No.
slide? Okay, maybe I can explain. So normally when we activate a row, we share its charges. If it's, let's say we store 1, bitline becomes 1, right? But it's a function of what we store over there. So when you activate multiple rows, it becomes actually the average of what you have. Similar to when you see like the M bit, but it's a bit, let's say, in the same subarray, but over there is the same subarray. Here we have neighboring subarrays. Now there's another thing over there in the equation. So basically, when you activate multiple rows, it becomes the function of V, A, and B in the upper subarray, and V, X, and Y in the lower subarray. And what that means is that that's the average of A and B. If, for example, both of them are 1, the result should be 1, right? So sense amplifier uses that. What sense amplifier does is it tries to understand the difference between the upper bit line and the lower bit line. Which one, so for example, if upper subarray's bit line has higher voltage, it becomes VDD and the lower becomes 0. So by using that, with carefully, let's say, initializing these cells, we can implement and OR in one subarray. Since over there we have sense amplifier which has not, and by doing AND and OR in one subarray, we can have NAND and NOR in the other subarray.
Yeah,
that's pretty much it.
But there are also some good animations in Smile's talk, I guess, right?
Yes.
So people can also take a look there. But yeah, but the key idea is as what Smile just presented. So we did tests on many DRAM chips that cover different revisions and also chip densities. You can see some information about them on this table from the 2 different manufacturers. And we observed that commercially off-the-shelf DRAM chips can perform 2, 4, 8, 16 input and NAND OR and NOR operations. And the good thing is that for 16 input and NAND OR and NOR operations, we have quite high success rate, more than 94%. So it's not like fully accurate. There are some cases that we cannot get the value, like the correct value, but it's good that without doing anything, by using what we have commercial off-the-shelf DRAM chips, still you can have such operations. And might be useful for some application as well. Yes?
Is this the success rate for entire rows or for cells in the rows? So do you have like 6% bit flips, or do you have 49% entire perfect rows?
So yeah, I always forgot the exact definition of success rate.
It's
maybe
per cell, per
cell,
DRAM
okay.
cell.
Yeah.
We just want to understand if we can do that in DRAM cells. But
Okay. So
in
it's
the
not usable, really.
Yeah, in the another word, we use what you said in a row, how many of them are correct, etc.
Yeah. Yes.
Why are those failures coming?
So I can provide some insight, but maybe Ismail can continue. So basically, one issue can be like the design of also sense amplifier. So we are relying on the sense amplifier such that it can basically, find the difference nicely between the source subarray and also the destination subarray. So that the implementation of AND and OR is quite dependent on how sense amplifier can accurately differentiate between the voltage in the in the source subarray and also the destination subarray. But so not all sense amplifiers are perfectly designed. I mean, because of the process variation, and it can happen. So that's my try. But maybe you want to add something.
I mean, that's true. One other thing is that also process variation. Not all cells have the same capacitance, same
That's also
power. For example, assume that in the basic one, measured it of 3, right, A, B, C. If A is 3 times stronger than B and C, the result will be incorrect. So it's inevitable in DRAM that we will always have process variation because of the manufacturing process. And also one keynote over there is that we are operating beyond manufacturer recommending timing parameters. So here, this is not officially supported by DRAM. It's just we are trying to find a way to hack the DRAM to get these operations. So probably that at least I believe that if we have the official support for that, we will observe a higher, let's say, success rate. One example could be that we issue act per act, meaning that we first open one row, then we issue back-to-back per charge and act to open other rows to, let's say, play with the decoder circuitry to activate multiple of them. So basically, it's directly not simultaneous, but as if it's simultaneous. So it also has a role in here. A lot of things. Basically.
Yeah, exactly. It's process variation as well as also we are doing things that we are not supposed to do with DRAM chips. So the fact that they can also do this computation with quite high success rate is also quite interesting. Any other question? But these were really good questions. Okay. So yeah, we also showed that by violating the timings of DRAM chips, there are some cells that they always fail. So you always need to obey some timings if you want to read correctly from DRAM chips, basically, right? So once you violate timings, meaning that you reduce, the amount of time that you need to wait for, let's say, activation, then there are some cells that you still can read them correctly because of the process variation. So basically we have some kind of guard bands. But there are some cells that they always fail. So when you reduce the amount of timing by doing some profiling, at some point you're going to see that there are some cells that they always fail. And that's actually quite dependent on the physical or process variation of that DRAM chip. So by profiling your DRAM and finding those cells, you can actually come up with unclonable, like physical unclonable function, which is like signature of your DRAM chips. So whenever, for example, you want to make sure that the DRAM chip that you are accessing is the correct DRAM, you can actually query this physical unclonable function. So you record it, and then using this DRAM latency path, which we proposed, you can have the signature of DRAM also stored in the DRAM, and then you get this, and then you compare. And if things are okay, you can trust your DRAM, and then you can continue. So we can even use, in processing using DRAM in order to provide physical unclonable function, which I already discussed. So if you want, and that's actually very high level. So if you want to learn more about it, you can check this paper from Jeremy. And we also show that if there are some cells that when you reduce the timing, when you violate the timing, they fail randomly, which is quite interesting, meaning that they may fail or they may not fail. So, and then you can use that as a signal in order to generate random numbers, which is quite useful for many other big applications. So that's why we can also use like in DRAM like operations by violating timings in order to provide in DRAM true random number generations. If you want to learn about it, you can check this paper, DRANGE. We also show that Atterberg showed that by activating 4 rows at the same time, you can do this quark TRNG that provides even that improves the throughput of the true random number generation inside the DRAM. So that's another improvement on top of it. And NISA also did a system design, like end-to-end system design for DRAM-based true random number generations that you can check if you are interested. But doing a processing using memory is not only limited to DRAM, as you can imagine. It can be also using flash chips. And in this work, Flash Cosmos, we show that by benefiting from inherent computation capability of NAND flash memories, we can do in-flash bulk bitwise operations. Like by activating or by sensing, but in the terminology of flash chips, by sensing several word lines in a block of flash, you can do AND operations. And if you do this several like multi-word line sensing across blocks, you can do OR operations. And then also you can do inverse read and you do implement NOT operations. And combination of AND and NOT, you can have NAND and NOR. And you can also implement XOR and XNOR inside the flash chips. So the SSD that you have and the flash chips that it has inside, they are capable of doing computation. And we show that using real flash chips, actually, that you can do that with quite good accuracy and performance. So if you want to learn more, also I would recommend you check this paper. And if you want to learn more about PIM, I mean, in general, like yes.
Just one more question.
Sure.
This might be a stupid question, but
no.
I really don't know. For what applications do we commonly use bulk-wise bit operations? Because I only know like bulk-wise arithmetic operations from ML and stuff.
Yeah. So bulk bitwise operation actually is quite useful for many applications. Like one example can be actually, if I want to get back to what I was presenting before, SISA. So we discussed that we can actually implement graph algorithms like graph mining using set algebra, and then you would have set union and set intersection. And union is exactly equivalent to OR, and intersection is AND, right? So then you have bulk bitwise operations. That's one example, which I just commented. But there are also many other examples. Usually in our paper, we say that bulk bitwise operations has function in, I don't know, many applications like cryptography, hyperdimensional computing, yeah, and so on and so forth. I cannot remember now. But that's a great question. Okay, so if you want to have a big picture of processing memory and like, you know, what are the categories, what are the challenges, opportunities, you can always check this book chapter that we wrote in. We are also releasing the new version of it, hopefully soon. So stay tuned for that as well. So let me also quickly go through enable adoption of processing memory, and then we can conclude today's lecture. So processing memory is great, as you know, as you can see, but there are many challenges that we can address, we should address in order to see adoption of processing memory into the computer system. These are some examples, like applications and software for PIM. We need to think about it. What are the applications that they can benefit from PIM? Ease of programming is also an important thing. So you need to come up with the solutions or designs that they can basically make sure that you can program for PIM much easily. System and security support is another important problem that we need to address: coherence, synchronization, virtual memory isolation, communication interfaces, and so on and so forth. Runtime and compilation systems for adaptive scheduling, data mapping, access and sharing control, as well as infrastructures to assess benefits and feasibility. I mean, all these things are like, they are potential barriers to adoption of PIM, as well as they are opportunities, I guess, to do research and do exciting works for the future. And Safari, in Safari, we have done also a lot of works in all these areas. Like ease of programming, we basically publish several works, the SIM-DRAM, MIM-DRAM, Simple PIM, for example. For system and security support, we have done work on coherence, like Conda, synchronization, Synchron, and for infrastructure to assess benefits and feasibility, we have done this DAMOVE work that is basic. DAMOVE is to categorize data movement bottlenecks. And for that, you can actually understand how you can benefit from PIM. But those are just examples, and there are a lot more opportunities to do research in enabling PIM into computer system. And all these can be solved with change of mindset for sure. And we need to revisit the entire stack, as we discuss a lot into in this course. Another issue that I also want to a little bit talk about more is security issues in processing memory. So does PIM make security better or easier? There are some questions. They're kind of open questions for now, but if you are interested, we can also discuss them now. Like, does PIM make security worse? Any thoughts? Yes?
Difficult to say, but with the recent things we've learned with the M2 and M1 device group, I think there's always potential to make a human error. So I don't think by design, not, but in implementation.
Any other thoughts? Yes?
I mean, I guess as most CPUs nowadays have some form of protection against power inference, and I guess DRAM chips probably don't have that yet because you're not supposed to use them for computing. So this is probably easier or possible with DRAM chips.
Yeah.
RowHammer has such problems in more computing there.
Yeah, for example, you can use Ambit to do RowHammer. Yeah. Yeah, these are really good thoughts. So yeah, so PIM actually can, you know, make security worse. It can also provide some access, which you were not supposed to have access in the past. Like, for example, like side channel attack. There are works that they do like cache-based side channel attack by understanding the access latency through the caches. But using main memory to do side channel attack is not really easy, because it's not easy to differentiate between the latency of accessing different kind of accesses into DRAM. But once we have processing memory, so you have an engine there, and that engine can use to provide some, you know, information to you, and that can basically cause some side channel issues. But do you think PIM can also help security? Yes.
I guess the most obvious thing was the signature of the DRAM profiles for authentication of the DRAM chips.
Mm-hmm.
But
Yeah.
also, for example, making cube, getting memory initialized with 0 could maybe do some helpful programming and working with making initialization of variables maybe less costly, which makes them maybe you can give compilers the option to zero out whatever, so you don't read maybe security information that was left in DRAM was not later initialized in the program.
Mm-hmm. Yeah. Yes.
I think Intel was doing that, but you can also like have the whole memory encrypted and then only decrypt parts of it, like go up very short memory, then make sure that you can't read secrets from the memory.
Yes. Any other thoughts? Yes.
I mean, since the whole path of the data is much shorter, you have reduced risk factors because there's just less to look at. So I guess it's probably easier to protect a smaller system than a larger one.
Mm-hmm.
If the data never moves out of RAM, you only have to protect.
I think this is also quite important because you don't move data out. So once you put your data on a bus, on a DRAM channel, like DRAM bus, like the memory bus, there can be other things that they can observe what's going on that bus and they can see. So once everything is happening inside the DRAM, probably you may have less vulnerability. Or for example, there are a lot of system components like caches, like shared cache, that's the source of basically side channel attacks. But once you are doing computation inside the PIM, you don't need to share things. You know, there can be a part of PIM which is just allocated to an application, and that can be just executed there without sharing anything. So that can improve security, for example. So it's not. So when you think about security, PIM is like has some upside and downside, and that makes it interesting to study. So there are, as you clearly mentioned, there are a lot of things that PIM can make security worse, but it can also make security better, which is good. So there are also some recent papers from our group that I will also show a slide for them later, but you can check them as well. So these are also some like answers to what we already discussed, but of course, what you also presented and you mentioned also, meaningful. So can PIM worsen security? Like it can like worsen or easier to induce physical issues like RowHammer, as one of you mentioned. It can also worsen or for new side channel attacks, like the hardware bugs as well, new threat models, since it's a new component that you have, so you can also come up with new threat models. And it can also, PIM can enhance security by less exposure of data and keys. Also, you can improve some operations like homomorphic encryption, which are quite costly, but using PIM, you can accelerate them. So you can have in-memory homomorphic encryption as well as cryptographic hashing. You can have execution of security functions like trusted execution memory. You can have support for security primitives like TRNG, POPs, encryption, and more or better isolation, virtualization. All these things can help security, of course. So there are like issues and benefits we discussed, like security analysis of PIM system. The design space is actually quite huge, like the study. So there are a lot of things that we need to study here. Like we have different types of PIM, like PNM versus processing using memory. Different locations where we implement PIM is like in cache, memory controller, DRAM, non-volatile memory, storage, remote, or some other places. It is general purpose or a special purpose PIM, like multi-tenancy or it's a single workload, concurrent host and PIM access, memory bus protection, and robustness issues like RowHammer, RowPress. So there are a lot of things and so on and so forth that you need to consider. And each of them by itself can be actually a different work to me. And of course, PIM, basically PIM support can support more or secure execution of workloads. That's a question, but we need to look into it with a lot of detail. So if you want to get some idea about it, this is one of the work that we have done, that we use this real-world processing memory system, OPMEM, to implement homomorphic encryption. So you can check this paper if you're interested. And also this is in the side of Vorsen sites that Konstantinos and Nisa lead this project. And they show that basically PIM can amplify main memory-based timing covert and side channels, which this work is actually quite interesting. So I really recommend you to check it. And if you want to learn more also, you can check this short talk from Professor Mutlu. Let me conclude quickly. So we discussed about three major limiters to computing, like technology scaling is not going well, system complexity is increasing, old methods not keeping up, and processor-centric design are not keeping up. And these affect all metrics we care about, and these have fundamental impact on security and how we build secure systems. And we need to revisit how we build in architectures and how we secure them. I like to acknowledge all the support that we got from industry. These are some of the fundings. Blue ones are probably more, let's say, related to these projects, but thank you to all of them. And acknowledgement to all Safari members that they have done great research and they are doing great research. If you want to learn more about Safari, you can check our newsletter that we have. We are releasing it like usually once a year, sometimes twice a year. I think this is the latest version in, no, this is the latest version. In July 2024, you can check and learn about a lot of news going on in our group. And as a reminder, all these papers, talks, and artifacts are available on Professor Mutlu's website, our YouTube channel, as well as GitHub repository, that we open source tools and artifacts of our research. Any other questions? Yes?
What is the relationship of PIM and transactional memory? Just from thinking about it, it kind of seems similar. And so I was just wondering if there's some relation between those.
So transactional memory is the memory design that can help you to keep record of transactions, basically, right? Such that when you want to roll back to a previous transaction, you know, you can easily do it. It can also be implemented at the software layer. There are also some, like the hardware support. The only relation that I can think of now is that PIM can help you how you basically record your transactions in the memory and how you want to switch back to previous transactions if needed. If you want to roll back, for example, to recover from a fault or issue. So I think PIM can help with that by rolling back. Maybe you can use row clone to, you know, move data which is in another place to the place that you are currently needed. But yeah, of course, that's kind of relation to me. But yeah, any other thoughts you have on it?
No, I just wanted to hear maybe there was more.
Yeah, okay. Any other questions? Okay, so with that, I think I'm done with the first part of this lecture. We should have a break, let's say for 12 minutes. And we can get back at 5:25 with the genome analysis lecture. Okay.
Okay.
Hello, is it working? Hello.
Can 15 analyze?
Mohammed, which time we said we can start?
I said 25.
25. Should we? Yeah, that's true. Okay. Okay, good then. Then yeah, let's get started. So our challenge was going to be to cover, I guess, around 150 slides in 30 minutes. But he just came to a conclusion that I'll probably cover other half or maybe more than half of the slides in the next week, hopefully. So I'll go a little bit slower than I planned, which is nice for everyone, I guess. Then yeah, with that, so today's lecture, this part of lecture is about slightly different than what we've been covering so far. So this is about genome analysis. We're going to cover essentially what is a genome analysis is and what sort of algorithms we have and what sort of hardware designs also we have to do this genome analysis. But before that, I want to introduce myself. I'm John. I'm a senior PhD student in the Software Research Group and also lecturer at ETH Zurich. My research interests lie in the intersection between bioinformatics and computer architecture. And as Mohammed already showed in the previous part of the lecture, you can get to know us and our group using these links over there. So agenda for today, we're going to start with the introduction to genomics. So how can we analyze the genomes? And then I'll show you step by step how we do it in lower level. But essentially, I want to motivate you with essentially we need faster, scalable, and accurate genome analysis. And there are many reasons for it. One big reason is the genome analysis really helps us to understand the genetic variations between individuals. So we can look at the variations between genomes within individuals, and then we can perhaps even associate diseases to those variations, which are really important to develop perhaps drugs and to even provide solutions to these diseases. We can also understand the differences between species, right? We can maybe even find the common ancestors between species and also try to understand evolution. We can also predict the presence of maybe harmful pathogens living among us so that we can take an early action. For example, to have a surveillance of disease outbreaks, like it happened very recently with COVID outbreak, right? We can analyze the environment and then try to see whether there's a harmful pathogen is growing in an environment, and then we can take an early action to that. And of course, this is very important for personalized medicine as well. So imagine we can prescribe a drug, or even we can design a drug that is specifically tailored for you, right? That is specifically designed for you so that this drug is really effective for you. And there are, of course, like many applications that we will actually be covering today a bit. But then what is a genome? So every individual has one, right? Even like multiple copies of it, which makes us look different and maybe even have other phenotypes different than each of us. And then if you look closely, what you're going to see is that in every cell, we essentially have these, for humans, we have these pairs of chromosomes over there that you're seeing, which we call, for the human case, we call a diploid genome. So for human, we have these 33 pairs of these chromosomes, right? And if you look even closely, what you're going to see is essentially the double helix structure of the DNA, which includes essentially multiple nucleotides or ATGCs within the DNA. And this is basically how it looks like in a digital form. And basically, I'll then try to show you how large a genome is within a single cell. I usually ask basically whether you know whether you know like what sort of building this or which building this is, but I'll directly show you that for timing purposes. So this is Andreasturm in Zurich, and in the 16th floor we have offices over there. And essentially, if you sequence your genome, even like a single pair, even a single pair of your genome, which is coming from only from one of your parent, and then write every letter, basically, character by character on A4 size letter. And then basically, if you start from the beginning and when you reach at the end, and then if you stack all these papers together, what you're going to end up getting is basically the stack of papers that is high as basically this Andreasturm. And if you're curious, I did the math over there. This is really correct. So you can see basically how large, even less a genome, how large of an information we have even in a single cell of an individual. So we really need to analyze this data. We really need to deal with this data somehow. And then since this is also a very important problem, people try to basically construct the human genome from scratch. And then this process essentially started around 1990s. And then we first had our first almost full human reference genome in 2003. And since this was basically a huge deal, so this took around 13 years. It cost around $3 billion US, and many, of course, researchers worked on that. And then we basically thought, okay, we cracked the code of human genome. Now we can solve all the problems, which was not necessarily correct because that reference genome was not really full. And as basically the technology developed, as the algorithms developed, and as the researchers worked on this problem, we finally sort of essentially constructed the full, really full reference genome of a human a few years ago. And then these individuals, since this was also very, let's say, a big deal, these individuals were selected as the as one of the 100 most influential people in 2022 by the Time magazine. So we've been talking about the human genome. So we can basically ask maybe what about the other species, right? What about the other genomes? What about their sizes also? So here you see basically the size of a viral genome. The viral genomes are usually small. So in this case, we have a few kilobase long genome here. So this is a bacteria, which is actually a very harmful bacteria. I hope no one gets it. But the size of the genome is around 5.5 million bases. And if we switch to human, our genome size is around 3.2 billion bases coming from a single one of the parents. So at this point, maybe you may be thinking that, oh, okay, so as the genome size increases, maybe somehow the intelligence or whatever, the complexity of life is increasing. But if you're saying this, just think again. This is an onion, and it has a much larger genome than ours. And we have much larger genomes, which are around 150 billion bases. So you can already think that like this is essentially a very challenging problem to solve because the size of the data is really huge. But essentially, so then we have this DNA, right? And I really like this analogy, although maybe this is not extremely accurate. How is this DNA useful, right? So how a living cell makes a use of it. And for that, I usually use the analogy of essentially coming from the source code and then until the moment we execute it. So the DNA is really like a source code. So it has this useful part, but it also has like other parts that are not so useful, maybe like some commands and so on, right, in the code itself. But then later what we do is we transcribe it to RNA. RNA is really coming from the mostly useful parts of your DNA, like the assembly, right? It will use basically the functional part of your code, and then it will convert it into an assembly code. Then the translation happens, which then the RNA is synthesized into protein, which is really the functional part of your cells, as if similar to basically how you move basically instructions to your chip so that they get executed, so that they make up meaningful, let's say, numbers or meaningful results for you. And then basically analyzing the genomic data is important for many reasons. For example, you can, as I said, you can compare individuals to a particular population and then try to essentially come up with this statistics where whether a particular group is prone to a certain disease just because of a particular variation that they have in their in a particular region in their genome, right? So you can simply compare the individuals that have that particular disease to individuals that look healthy, and then try to find the differences between them. And then these differences really can point out to these diseases. And then you can also get your genome sequenced. And then there are these databases available. These are open source. And then you can really figure out the variations you have in your genome and then go and check these databases, what these variations mean, right? Maybe you have a particular variation that makes you, more prone to having a particular type of cancer. And then you can look for it and then see whether this is really the case. And of course, we have not just basically very small variations like a single character variations. We also have much larger variations. Essentially a huge deletion or insertions can happen in your chromosomes, which can cause, again, different types of diseases. And essentially, basically understanding the genome, analyzing the genome has many applications. For example, we can now today edit the genome, right? We can go and pinpoint a particular location in your genome, and then we can change it. We can alter the content of that genome. This is really basically impactful because, again, as I said, if you are prone to a certain disease, we can go to that particular location in your genome, and then we can sort of tune that functionality off so that you won't be prone to that disease anymore. And since this has basically many implications, like a huge impact in the field, these individuals who showed that this genome editing is programmable, meaning you can actually target almost any region in your genome and then alter the content of it. They got the Nobel Prize even within, like, I guess, 7 or 6 years after publishing the paper that showed that essentially functionality. And also, we want to do a large-scale analysis, right? Given a population, we want to understand essentially whether there are, again, maybe harmful pathogens in that environment or what are the differences between individuals. We want to do rapid surveillance of disease outbreaks. For example, genome analysis has been used for that purpose. We've used it to essentially understand the Zika virus, COVID-19, and also Ebola virus, and so on. People develop tests, for example, COVID tests, by simply purely using genome analysis. We can do in-field portable analysis. Imagine you attach your sequencer to a drone and then you let it run in a field and then it makes the analysis for you. It's a basically very useful information. We even use it, genome analysis, in outer space, right? Maybe even on Mars, to understand basically the impact basically of the outer space on the genomes and even more things. And also DNA is very valuable asset, right? So you really don't want your genome to be in harmful hands. And this actually has happened last year. I don't know if you know what 23andMe is, but what was happening is that people would be sending their samples to this company, and then the company would be telling you, okay, so we did the analysis and it looks like you have this and that, and maybe they would be even linking you to perhaps to your particular heritage. People would be figuring out, okay, like I see that I have this many sisters that I didn't know, and so on. And there has been even a Netflix series about it. But essentially, this data was not really private, and then the data got leaked, and basically, the really sensitive information now is on the hands of certain individuals that we don't know what they are aiming for. And you can even think of maybe in the insurance case, maybe in 10 years or 20 years, you go to an insurer and then you try to have an health insurance, and then somehow you have a, I don't know, high estimate for your health insurance, and you don't know why, but they know why, basically. They know that maybe you're prone to a certain disease, and maybe that's why they are giving you a high, essentially, estimate, right? So this can be really harmful, and this is a really sensitive information to protect. And also, people are even thinking about how can we shop using our DNA, right? So imagine you go to a grocery store and you don't know whether you are basically allergic to a product. So you just basically scan the barcode, and whatever the companies you're using, they already know your genome, right? And then you scan the barcode, they automatically tell you, okay, you're allergic to it, don't buy it, and so on. So again, so there are many applications basically, given that very sensitive and useful data. So I'm trying to motivate you basically why this is very useful and why people are using it. And people are now even using DNA to do the computation, literally. So they are designing the problem in a way that a DNA will make a certain connection such that that particular connection will give you an answer. They are using it, for example, to solve the traveling salesman problems, to solve even like essentially NP hard problems, because you have a huge parallelism over there, so that you can combine this, utilize this parallelism to solve really hard problems. Again, applications are really limited by our imagination, and I invite you to even think about even more applications. But then the other question is, then essentially how and where to enable fast, accurate, cheap, and scalable genome analysis, right? And then we see this common problem today. So this is a special purpose machine which is generating the sequencing and genomic data. And this is really specialized at generating data at a really fast rate. So it is really good at basically generating data at a fast speed. But then to analyze this data, we're trying to use this general purpose machine, which is really slow. And the reason why it is slow, because it doesn't really know about the requirements and the needs of that particular data, right? So that's why it looks scared over there, because it doesn't know what's coming. So for that, we're essentially looking at the different architectures and then asking the question, given the type of the data, so this is not really specific to genome analysis, right? But given that we're now in the lecture of genome analysis, given that sequencing machine, what sort of architecture should I use? Maybe even a heterogeneous system that includes multiple of these hardware to perform the analysis in a fast and energy efficient way. Maybe even like for mobile solutions, that you can attach these sequencers to your mobile device and do the computation there. And there are different requirements for that. And of course, to achieve this, as you've seen this many times, we look at basically the entire stack of computer architecture and then try to co-design basically everything all together so that we can optimize the performance, accuracy, and the energy efficiency. So if you are interested in learning more about how we essentially co-design algorithm and architecture together for genome analysis, you can take a look at this paper to see what sort of efforts we have in that direction. But we believe there's a bright future for intelligent genome analysis, meaning we need to co-design hardware and algorithm together so that we can improve the performance and energy efficiency. So with that, I'll start quickly perhaps covering some steps in genome analysis, and whatever remaining is, we're gonna cover them in the next week. So I'll first start with how we essentially, I'll give you an overview of the genome analysis steps in genome analysis, and then perhaps start with how we generate the sequencing data. So it all starts with essentially with the sample collection. This can be perhaps your blood sample, right? We may be taking a swab from your mouth and then essentially analyzing it. Then, so this DNA is not directly in a let's say, analyzable form. So we sort of modify it so that we ensure that this DNA can talk to the sequencing machine in the right way. And then the DNA is then inputted to the sequencing machine, which will give us essentially the digital data that we want to analyze. And all of these computational steps are essentially located over there. So there are essentially many steps in genome analysis. It starts with the data generation. We get the DNA molecule or RNA molecule, and then we essentially generate the raw data. And then we somehow process that raw data to put it in a meaningful, analyzable form. And then we perform some further steps to basically analyze it and then to extract some, generate some insights from this genomic data. So I'll start with how do we basically start with a molecule, biological molecule, and then generate the data in a digital form. So for this, we use these machines that we call high throughput sequencing machines that essentially takes this biological molecule, which can be a DNA or RNA, as input, and then as output, it will generate these fragments or sequences from DNA that we call reads. So these are really essentially fragments from the DNA. It's not essentially the full part of your chromosome, which then creates certain challenges for data analysis. So one challenge is, once we create this digital data, we don't know essentially the origin locations of these sequences in the genome, right? So the one goal would be to identify where they are coming from in your genome. The second is, these sequences are not fully accurate. They're going to contain errors that are perhaps introduced by the sequencing device due to their imperfections. And essentially, we have many of these sequences that we need to analyze quickly. So these are essentially the challenges we're trying to solve. And to generate the sequencing data, there are many technologies. There are essentially many machines. For example, Oxford Nanopore Technologies, PacBio, Illumina, and so on. So I'm not going to explain all of these, but only focus on one of those. But essentially, the key here is that given a sequencing technology, given a sequencing device, they all generate different types of raw sequencing data. For example, Illumina generates sets of images that corresponds to ATGCs at a particular location in your DNA. So you look at the color and then say, given that color, or this must be A, and so on. Nanopore generates electrical signals, which we will actually cover a bit today. And PacBio essentially generates streaming, let's say, images that is in the format of a movie, again, similar to the idea in Illumina. In Safari, we're looking at these newer genome sequencing machines and then try to understand their limitations and then see what the opportunities are. So if you are interested in essentially the steps that we do perform in the newer genome sequencing devices, you can take a look at this paper. So as I said, sorry, go ahead.
Is there a reason why there's use of images and movies? Because you just need ADCGs, right?
Mm-hmm.
Why are we encoding them? Why are they encoding them in images and movies?
Mm-hmm. So this essentially is because the technology that you're using, the underlying technology that you're using in these devices, sort of work in that way. For example, in Illumina, what you're essentially doing is you are inserting a single base. So imagine you have a single strand of DNA, ATGCs, right? And then there are other ATGCs that are floating around. And then if you know a little bit about biology, you may know that when you have an A in one strand, the corresponding part of it will be T, right? So if there's a T that is floating around, the T will attach to it. So they designed that T in such a way that as soon as it attaches, it actually also releases a photon at a certain frequency. So the goal would be essentially to capture that photon, and which are basically the colors over there. So given that frequency, actually, you can tell this is A. And then looking at that color, you can say, okay, this was A, and so on. So this is really about basically what sort of device that you're using at the lower level. Any more questions? Okay, probably I promised you I would go slow, but I guess this is not in my genes, I guess. Probably we need to analyze. But anyways, so I told you that I'll slightly cover the sequencing data generation and focus on nanopore sequencing because, in my opinion, particularly this one has many interesting opportunities going into the future. So this is how one of the nanopore sequencers look like. This is really small. So this is handheld. You can really fit it in your palm and then connect it to your personal device. And basically what it includes is basically there's a flow cell. You insert your DNA somewhere here, and then these microscaffolds, which we call nanopores, essentially, will read each DNA somehow using these nanopores, and then will tell you the output as electrical signals. And I'll show you actually how it works. But this is basically our overview of what it looks like. But then it didn't really start as sophisticated. So I showed you a picture maybe like that was developed 5 or 6 years ago. But the idea of nanopore actually really started in 1989. Based on basically a very simple idea that was written on a notebook of David Deamer, which is basically really about a simple imagination. Given you have a DNA which is negatively charged, right? The question is, can you somehow drive it through some tiny pore where the other side is positively charged? And as you drive it, from the negatively charged side to the positively charged side, can you somehow basically understand the ionic current disruptions, right? Because as the movement is happening, the current, whatever the current you're applying over there, will be disrupted. And then the question was, is this disruption basically useful enough for us to tell each base, each nucleotide over there so that we can sequence the entire DNA? So this was a brilliant idea, but it didn't work back then. The reason for that, we couldn't really basically sequence every base. And the reason for that was you cannot really control the speed of DNA over there. So when you put the DNA on the negatively charged side, and then when you let it flow towards the positively charged, it will essentially flow somehow in a stochastic speed, which is essentially very high, so that you cannot really capture the ionic current disruption for every base. So that was the challenge back then. But then essentially people worked on this idea for many years because this was essentially very promising. And probably I don't have a slide for it. Let's see. I guess, yeah, we have over there. So, and essentially a company called Oxford Nanopore Technologies came up with this protein, which is a motor protein, which is their actual trademark. So what it does is essentially it attaches to the end of the DNA, and then it sort of guides it through one of these nanopores. And then when the attachment happens, it will essentially control the speed of DNA at a certain speed. And the speed is around 400 and 450 bases per second. And then you can essentially sample the ionic current disruptions even at a very fast rate, which is usually around 5,000 samples per second. So this means that you're getting 10 electrical current readings per base, which is good enough for us basically to tell what sort of base that we're reading, looking at the electrical signal. And this is basically a widely used technology in the field. One big advantage is that it can produce reads fragments of up to length of 4 million bases, which cannot be done by other technologies. It has the opportunities of portable sequencing. You can carry it around and then do the sequencing. It is relatively cost effective. And it has this unique feature that we call real-time analysis, which I'll show you now. But before that, maybe I can visualize how nanopore works a bit better here. So here what you're seeing is maybe a 3-layer solution. On the top layer, we have a negatively charged site. On the bottom layer, we have a positively charged site. And on the middle, we have a membrane. And then a nanopore basically is then attached to that membrane, which is basically a tiny pore, which is tiny enough just basically a single strand of DNA can pass through. And then you apply the voltage in a certain direction that the top part becomes negatively charged. And since the DNA is also negatively charged, and what's happening here is that the DNA is literally moving from the negatively charged side to the positively charged side. And as it moves through that tiny pore, specifically the narrow head area that you're seeing, which is called sensing head, as it moves through that region, the ionic current that we're applying is disrupted. And we're measuring these disruptions and then reporting them as electrical signals at a certain speed. And then what you can really do is that as soon as this data is generated, you can start analyzing it. So you don't have to wait for the entire sequencing to finish. Rather, you can start analyzing it. Maybe you translate it to the ATGCs, or maybe you can even use these electrical signals for analysis. But one really good advantage of nanopore sequencing is, based on your real-time analysis, you can actually even talk to the sequencer. You can give feedback. And then perhaps even say, oh, I don't want to continue sequencing that particular read, because maybe you figured out that this is not really useful for you anymore. Maybe it is coming from, I don't know, a viral genome that was contaminated in your sample, and you're just interested in the human genomes. And then you say, okay, I don't want to sequence it, and then you stop sequencing it. And then this is not really magic. How it happens is that when you send the signal, there's basically a short fraction of time where you essentially start applying the voltage in the other direction, such that now the top layer becomes positively charged, so that now DNA starts moving towards the upside, so that it somehow is ejected from the nanopore. And then since it no longer contains like certain, let's say, attachments at the end of its set, it will not essentially bind to that nanopore ever again. So this is basically the advantage of it. I guess maybe I have 10 more minutes, I can continue. So this is basically,
You said earlier that some errors will happen. And how can we know when there's an error or how to correct it if we don't actually have the ground truth?
So that is also a very good question. One type of error that is sort of linked to the sequencing technology that you're using is called skip error, which is essentially, I told you that we can control the speed and we can actually control the speed in maybe a very deterministic way nowadays, but still there will be some fluctuations and sometimes the DNA will move very fast. And then if that happens, essentially you lose whatever the information over there. Or maybe you will just simply, instead of generating 10 samples per base, maybe we'll just generate 2 samples or 1 sample per base, right? Then you'll have a low amount of information. So to understand such issues, people usually use other types of sequencing technologies, really extremely accurate ones, but extremely costly and slow. And then they sort of use them as, let's say, ground truth. And then they develop these either ML-based, machine learning-based techniques or other type of statistical analysis to sort of link, essentially, if you have this type of raw signal and if you translate it and if you're seeing this and if this is an error, let's go back what was in there in the raw signal, let's try to understand what was the pattern and so on. So there are usually statistical approaches to it. And you can even correct after translating it. These are usually called hybrid approaches, where you have sequencing data from, again, multiple technologies. And the idea is maybe only one of them or 2 of them will contain errors, but the others should be accurate. So you sort of generate the consensus between them to correct those. Sure.
Do these machines contain arrays of nanopores for redundancy? They do, right?
So there are multiple number of channels. The reason for that is not necessarily for redundancy, it's for parallelism. But we also copy the DNA multiple times to generate redundancy.
Okay.
So that's the other side of it.
And how can the real-time computations happen? Because this needs to be synchronized. We need to have a real-time DNA processing and make decisions real-time. So we need to look at the same thing, the same part of the genome at the same time to make real-time decisions, because we don't know.
The answer is you don't actually have to wait for others to sequence. As soon as one of them is, let's say, sequenced, you can maybe map it to a reference genome, and maybe the other will come later on, and then you say, oh, this one also maps here. So. Are there other questions? Okay. So yeah, this is nanopore sequencing, and I'll quickly show you how we utilize this raw data, again, focusing on nanopore data. There are usually 2 ways of it. One is translating the data to ATGCs, and then you do the analysis based on that. Or you somehow analyze the raw data directly by doing some denoising and so on to reduce the error as much as possible. So most common way, most traditional way is to translate this raw data, which we call base calling, to bases, to the individual DNA characters, which are ATGCs. And then you can do your usual analysis after translation. So we know that this type of analysis we call base call analysis is usually less noisy because it uses these powerful, especially DNA-based computations, which can be really accurate for translation purposes. And of course, there are many analysis tools that is developed for translated data, because this sort of creates an abstraction for you, right? ATGC is not necessarily technology dependent. So it can be coming from any technology, but then you can develop almost any tool to analyze these ATGCs. Rather, the raw data would be sort of technology dependent. But essentially, in order to especially translate, you need to rely on powerful, power-hungry devices such as GPUs to do the translation, because they are really computationally costly algorithms. There are also recent approaches where they try to directly analyze the signals without base calling, without translation. So it's as if like you're removing the translator in between, and then your scalability and portability, because the computation reduces computation. And also we know that these raw signals or raw data retain more information than just bases. For example, they'll tell you somehow about the structure of the DNA, whether it is methylated or not, which is again about the structure, and about maybe the ions that the DNA is containing, so that you can, and they are somehow related to also, again, certain diseases, so that you can directly utilize this information in raw data. Yes, so this is the question: do we need a translator to analyze the genomic data? The answer is no. We can perform certain steps to put this electrical signal or those raw sequencing data in a meaningful way. So this usually starts with certain assumptions. Again, this is a bit related to the technology itself. So what you're seeing here is that is a nanopore and a certain part of DNA that is getting sequenced. And essentially, in a very low level, we're not really sequencing a single base at a time. So what is really happening is that there is this narrow head over there, and then whatever the base closes to that narrow head is disrupting the ion in the most meaningful way. But there are also other bases that is surrounding that narrow head, which is also disrupting the ion. So in a sense that actually we have K-many nucleotides essentially affecting the electrical signal that is that we're generating at a time, which we call like K-mer over there, many sequences, K-many bases in a sequence. And then this K-mer is done whenever we're sequencing that K-mer, it is disrupting the electrical signal in a meaningful way. And then whenever basically you have a new base that comes in and another base that comes out, we usually see an abrupt change in the signal reading. And then you can recognize those abrupt changes using statistical approaches, such as essentially t-test, students t-test, and so on, so that you can identify, okay, this is the K-mer that you're reading, and so on. And then you do some outlier detection, and then you assign some values to those. And then instead of basically analyzing ATGCs, you sort of analyze these numbers to perform genome analysis. So we published many works in this direction where we directly analyze raw signals instead of base calling them. This is one work towards that direction, RowHash, and the subsequent work, RowHash2. We also try to align the signals to genome so that we can identify the mutations directly, again, without even converting them to ATGCs. We also develop works that quickly translate the electrical signals to ATGCs by doing some optimizations on these neural networks. And also we do this type of base calling translation directly in the memory using Memory-Centric type of devices to do the computation again quickly. And also for error correction, we develop ML techniques to understand the errors and then correct them if they happen. So with that, this is the perfect time to stop. I'll stop, and perhaps next week we'll continue with the remaining 2 steps and how we accelerate these steps basically. Maybe if there are questions, I can take them before we go. Okay, then with that, thanks everyone, and see you next week.